Hi, this is Akash, and I'm with my teammate Divya to present to you the video review of our papers. We'll be attaching the link in the PPT so the reviewers can refer to it if at all they want to. So, without further ado, let's get going. Divya, on to you.
So the papers we have chosen are a multi-agent extension of a hierarchical task network planning formalism and hierarchical multi-agent reinforcement learning, which is basically HTN versus HRL, but in a multi-agent scenario. Now, before going to the similarities, we will briefly explain the work done in these papers, which helps in understanding the parallels we draw between the papers. So we very well know that we have established formalisms or representations for single agent planning problems like strips, PDDL, HTN, etc. And so far, whatever we have seen in Professor Rao's lectures deals with these. Now, what if there are not one but multiple agents in an environment? What happens now? Now, in this scenario, we struggle to name such formalisms. This is precisely what the authors in the HTN paper are attempting to solve, to provide formalisms for multi-agent planning with clear semantics. Let's start with the paper, a multi-agent extension of a hierarchical task network planning formalism. Now, multi-agent planning in the real world more often than not happens in a dynamic environment as opposed to a static one. So it is important to analyze agents in such environments. In dynamic environments, it so happens that there is no fixed state of the environment and fixed goal states. It may be the case that the environment brings in new pieces of information which the agent is unaware of, and so because of this, in order to survive the environment, the agent might have to change the plan drastically. So, a need of online planning arises. The authors have some demonstrations of their multi agent hierarchical task network formalism, which does all of the said things included in the paper. Now, I pass on to Akash to talk about domain representation.
Yeah, thanks, Divi. So, unlike single agent planning problems we have seen in the class, where the domain and the problem descriptions are already given, in this scenario, both of them have to be constructed or updated from a baseline during execution. Why? Because if you remember, Divya said earlier that the proposed formalism, which is the MAHTN, represents planning problems for online multi-agent planning problems, which means we have to be ready to encode changes in the environment and updated goals. So inevitably, this calls for a mechanism to observe these changes and construct the descriptions on the go. This mechanism, as the author call it, is a translator, which the agents use to translate their information about the world into domain and problem specifications that can then be passed on to the planner. Now, it is important to note that each agent has their own domain and problem specifications. This is because the author assumes three things to be true of this environment. Agents have incomplete knowledge or capabilities for solving the problem. There is no global control, and the information is decentralized. Now, this leads to a small problem. What if the actions are conflicting among the agents? What if one agent sets a predicate to false, which is actually needed by another agent? This could create a deadlock situation. To curb this problem, it is up to the developer to annotate those actions that can presumably cause conflicts. Primitive actions are always translated to operators in HTN. Thus, only operators can cause conflicts, and HLA or high level actions cannot. And likewise, dependencies between actions can also exist, either as concurrent actions which require another agent or actions of other agents to happen first. And because of this, MAHTN also supports dependency blocks to model dependencies, if any, from other agents. So to summarize, The domain description of MAHTN allows for defining conflict and dependency blocks on top of the normal definitions, which is taken from the SHOP2 Planner's formalism for HTN. Now, Divya, you want to talk about the problem representation?
Yeah, sure. So the problem representation of MAHTN, much like PDDL, which allows for type establishment, but these types come in the form of facts. They can be used to establish types and characteristics of things in the world. For example, location kitchen establish that kitchen is a location in the world. The initial states are used to represent what is true in the world at the specific moment in the time. For example, kitchen dusty represents that the kitchen is dusty. Goals can be listed as either ordered, that is, when the order in which the goals have to be achieved needs to be strictly followed, or unordered, that is, when we do not know the order and the planner is free to find any order between the goals. So, yeah, this is pretty much it for the first paper on hierarchical task networks. We can now move on to the reinforcement learning paper, which is also set in the multi-agent scenario. In this paper, the agent is made to learn three interrelated skills: how to perform each individual subtask, the order in which to carry them out, and how to coordinate with other agents. The authors also define something called cooperative subtasks, which are subtasks which enable coordination among agents and significantly improves the performance of the overall task. Because of the abstraction involved, according to the authors, the agents get to learn coordination faster at the level of cooperative subtasks rather than at primitive action level. A communication action provides the agent with the actions selected by the other agents at a cooperation level, but it has a certain cost associated with it. Therefore, before an agent makes a decision at a cooperative subtask, it decides if it is worthwhile to perform a communication action. Now, incorporating all these concepts, the authors define a hierarchical multi-agent reinforcement learning framework called cooperative HRL. With cooperative HRL, their goal is for agents to learn action and communication policies that together optimize the task given a communication cost. Now, Akash will talk about the problem formalization for HRL.
Yep. But before going into the problem formalization, we must first understand some more about the real world AI problems in general with respect to multi agent scenarios. The two main problems one often encounters in the scenario is one, the curse of dimensionality, that is, the number of parameters to be learned increases dramatically with the number of agents, and two is the partial observability problem, in which states and actions of other agents which are required for an agent to make a decision are not fully observable, and inter-agent communication is usually costly. In a scenario where cooperation is key among the agents, HRL is shown to solve these problems conveniently. How you might ask? It is because of the simple fact that hierarchical methods are an excellent framework for scaling RL greatly to large domains by using the task structure to restrict the space of policies. And because of the introduced abstraction, the communication overhead is also minimized, as it happens only in cooperation levels, which are generally higher levels of abstraction. Now let's get into the problem formalization. We know that in HRL, policies over primitive actions are semi-Markov when composed at the next level up. And since actions are durative too, semi-MDPs are used to model the problem. This means decisions are only made at discrete points in time. And the state of the system will change continually between decisions. Unlike MDPs, where state changes are only due to the actions. Since this is a multi-agent scenario, SMDP is extended to its multi-agent scenario equivalent called MSMDP. An MSMDP can be mathematically defined as a six-tuple, and as you can see here, those are the Y, S, A, P, R, and T, where Y is a finite collection of n agents, S is the set of states of the system being controlled, A is the joint action space of each finite set of actions which can be carried out by each agent, P is the action model or the transition probability function as we have learned in the class, and R is the state to reward function mapping, and T is the termination scheme. A termination scheme, by the way, is used to terminate temporarily extended actions at the same time. Only then can they be compiled into a joint action, which is required for the action model to work. Now, let's get into the specifics of how the hierarchical task decomposition takes place. First, the MSMDP, let's call it M, is broken down into a finite set of subtasks ranging from M0 to MM-1, where M0 is the root task and solving it will solve the entire MSMDP M. Each non-primitive subtask in the finite set has its own state space, initiation set of terminal states, set of actions that can be performed, and the reward function. Now that we have the task decomposition defined, let's look at the policy and its execution. Divya, want to take over?
Yeah, sure. The policy execution phase is fairly simple in this scenario. For the sake of argument, let's assume we have a policy for each subtask in the hierarchy. Then the hierarchical policy for pi for the task will be set of all policies from the root node, that is pi 0, to the mth subtask, that is pi m-1. Hence, the hierarchical policy is executed using a stack. Each subtask policy takes a state and returns the name of a primitive action to execute or the name of a subtask to invoke. When a subtask is invoked, its name is pushed onto the task stack and its policy is executed until it enters one of its terminal states. When a subtask terminates, its name is popped off the task stack, and if any subtask on the task stack terminates, then all subtasks below it are immediately aborted, and the control returns to the subtask that had invoked the terminal subtask. Now, of the cooperative subtasks, you might ask, well, we already discussed how the agents have to coordinate at the cooperation level to execute or refine cooperative subtasks. And because of this, we need to call the cooperative subtask to model joint action values. This can be done by an MSMDP, but the only difference here is the action set is the joint action set, which factors in actions from other agents as well. Having established the concepts and how they are represented, Akash will now talk about the algorithm itself.
Yeah, so let's get it going. Let me walk you through line by line. So let's go to the first line. So the sequence list you see in the first line will contain the actions performed by other agents, which belongs to the union set of those actions, which is in UL. This is because in addition to storing the states visited during the execution of a subtask in UL, which is S and S dash, an agent must store the actions in UL being performed by all the other agents to enable cooperation. The next couple of lines deal with the condition when the task Mi is primitive. If so, we execute action Mi in state S and land in state S dash and receive the reward for landing in that state. We then do the value update and push the state and the actions belonging to the UL and done by the other agents onto the front of the sequence list. It must be noted that the v-value updation here for the next time step uses standard temporal difference learning based on sample trajectories. And by the way, alpha in this equation is the learning rate. Now, if the subtask is non-primitive, we do the following. Choose a subtask according to the current exploration policy pi, generate child sequence, the subtask in the next level that is, compute the best possible action using C and B values, which uses temporal difference learning, where C is the completion function of the cooperative subtask Mi, and update the completion function for each state in the child sequence list. If the current subtask is a cooperative subtask, then the C function factors in the action of the other agents belonging to the set UL. And that is why you see a lengthy equation in the if cooperative action block. The two blocks discussed now feature in a while loop which runs till Mi terminates according to the termination scheme. And after the loop, the algorithm pushes child sequences onto the front of the sequence list. And in the end, the final sequence to be followed is returned. So yeah, that's pretty much it for the RL paper. Now that we have briefly explained both the HTN and HRL papers, let's get into the parallels that we could observe while reading through these papers. The first obvious parallel we found was just like the HRL case, or any RL scenario. The HTN algorithm in the multi-agent setting is learning the world model online. This is highlighted by the fact that there is a separate mechanism altogether defined by the authors called the translator, which is responsible for modeling the world changes. Also, it is noteworthy that the state space shoots up in both these scenarios. Due to the presence of multiple agents, and because they have independent partial models of the world, the state space also grows dramatically along with the number of agents. The last parallel we observe is that in both these scenarios, the models are designed in such a way that they capture, implement, enable coordination among the multiple agents in the environment. For example, the HRL paper defined a new subtask in itself called cooperative actions, which it communicates as a high-level action description with other agents. It does so at the cooperative level to minimize the communication overhead, as opposed to sending primitive actions. On the other hand, the HTN paper discusses introducing completely new predicate blocks in the proposed formalism in the form of dependency and conflict block. These blocks enable the domain writer to model cooperation at high levels of abstraction. So that's it for our review, and the links to the papers are included in the presentation. Thank you.
Okay,